part E we have to use, then by parts E and F of proposition 3614 we have this. In the beginning itself I am taking cardinality a to the power b to the power c. Note that by part F, a to the power b is the cardinality of this set, and a to the power b to the power c is the cardinality of this set, this entire set. So we will have a to the power b to the power c, but I cannot write it in that way. I have to argue step by step. A is the cardinality of A. Okay, so let us go in that way. This is the cardinality of B to the power, this is the cardinality of C. Now we apply part F. Okay, applying part F, this becomes equal to cardinality of a to the power b whole to the power cardinality of c. Again, by applying part F, we have and now this thing has the same cardinality as this set. This follows from the previous paragraph. And what is the cardinality of this set? First, if you apply part F once again, then this will be cardinality of A to the power cardinality of B cross C. And if you then apply part E here, you will get this, and this is nothing but a to the power bc. So that's how one of the rules of exponent has been proved. To prove the other one, we are going to show just like this one, that two sets have the same cardinality, and it goes like this. Let D, E, F be sets such that E and F are disjoint. Whatever they are disjoint. We claim that D to the power E union F and D to the power E cross D to the power F have the same cardinality. This is our claim. So we will have to produce a bijection. So we are directly going to define it. Define U to be a function from D to the power E union F to this by u of f. What is f? F is an element that is coming from the domain, which itself is a function from E union f into D. What if I write like this? Where the first coordinate is the restriction of this function. Since it's a function defined on E union f, we can restrict the function to the subset E. Also, we can restrict the function to the subset f. This first restriction will be a function from E into D. The second restriction will be a function from f into D. So their ordered pair is actually an element here. And for a given function f, these restrictions are well defined and unique. So that's why clearly u is well defined. We now prove that u is 1 to 1. Well, instead of actually proving, there are many things actually, okay, I will have to carry out the proof. Let f and g be two elements in this, such that uf is equal to ug. We have to prove that f is equal to g, then u will be 1 to 1. This implies what? Restriction of f to e, comma, restriction of f to f equals restriction of g to e, comma, restriction of g to f. Okay, we have simply applied the definition of u, or the corresponding components will be equal. So this will be equal to GE and this will be equal to GF. That means the functions f and g agree on the subset E. Also, they agree on the subset f. So that means they agree on the whole set E union f. These equations imply f and g agree at all points of E union f, that is f is equal to g, because for both of this function E union f is the domain, and that proves that u is 1 to 1. So u is 1 to 1 or injective. In the previous one, of course, it was quite complicated, but in this one it's not that difficult. Next, we prove that u is surjective. Next, let let us take mu, comma nu be an element in this. So that means mu is a function from E into D, nu is a function from F into D. define a function, say theta, from E union F into D by this formula. Theta of x is defined to be equal to mu of x if x belongs to E and nu of x if x belongs to F. Mu and nu themselves are well-defined functions, and these two parts of the domain do not have any conflict because they are disjoint. So that's why theta is well-defined. Note that theta is well-defined because E and F are disjoint. Hence, theta is actually a function in this set. Now, what is the U image of theta? By definition, the U image of theta is an ordered pair where the first coordinate is the restriction of theta on E and the second one is the restriction of theta on F. Now, if you restrict theta on E, it is nothing but mu, because that's what it is. On E, theta is nothing but mu. So this is equal to mu. Just like that, the restriction of theta on F is nu. So the arbitrary element we have chosen in the range of U has now been expressed as a U image of some element theta in the domain of U. Thus, U is surjective. We have thus proved that this and this have the same cardinality. And now we are going to use this to prove the other rule of exponent. We have already okay, anyway, so now let us take three sets. Let D be the set of all natural numbers lying between 1 and A. E be the set of all natural numbers lying between 1 and B, and F be the set of all natural numbers lying between B plus 1 and B plus C. Why do we suddenly take a thing like this? It's because note that unlike the previous one, here we have an extra condition. E and F have to be disjoint. So here they are disjoint. here all the elements are less than or equal to b, here all the elements are greater than b, so there can be no common element. Note that E and F are disjoint and cardinality of D is A, cardinality of E is B, and cardinality of F is C. Although it's not immediate, but you can see that there is a natural bijection between F and the set of all natural numbers lying between 1 and C. There is a bijection, and that's why they have the same cardinality. That other set has cardinality C, so this one also has cardinality C. Now, okay, here however, what are the parts of proposition 364 we need to apply? Part E and F, and along with that part B also. So now by parts B, E and F of proposition 3614, we have what do we have? We have to now prove a to the power b times a to the power c. Okay, so this is cardinality of d to the power cardinality of e cross cardinality of d to the power cardinality of f. By part f, these factors become these: cardinality of d to the power e cross cardinality of d to the power f. By part e, this becomes cardinality of d to the power e cross d to the power f. By the previous formula, this is the same as the cardinality of d to the power e union f. Again, by applying part f, we have e union f. Now in that exponent cardinality, we apply part b because e and f are disjoint, so this is equal to e plus cardinality of f, and this is a to the power b plus c. So that's how we have the other rule of exponent also proved, and this completes the solution.